Let's look at number 2 off the AP FRQ review. Related rates. Number 2, no with calculator. Water is poured into a tank in the shape of a cone that's 24 feet tall, and a diameter at the top of the cone being 20 feet across. Part A says write the formula for the volume of a cone of water in terms of H, the height of the water in the tank. So we know the volume equation is 1/3 pi r squared H, and we want to be able to get this equation in terms of H. That means we want to replace away the R. Okay. First things first, though, let's create a similar triangle proportion that we're going to need that will help us find that relationship between the radius and the height of the water level. So because we know the diameter at the top of the cone tank is 20 feet across, then the radius must be 10. So I'm just going to go ahead and indicate that with 10. The height of the full cone tank is 24 feet. And then the R and the H represents the radius and the height of the water level. So we can say this. We can say there's a relationship between this triangle and this triangle. They are in proportion, in a similar triangle relationship there. So we can say R is to 10, little radius is to the big radius, as little height is to the big height. So R over 10 equals H over 24. I'm going to cross multiply here. I get 24R is equal to 10H. I'm going to solve for R because that's the variable that I want to eventually replace away. So divide both sides by 24. 10 over 24 reduces to be 5 over 12. I'm going to replace R with this 5 over 12H. Now, careful, that squared is still there, so 5 over 12, H is going to be, this expression is going to be squared. And then let's expand this out. So we can square the 5, square the 12, square the H, and we get 25 over 144, H squared, times pi over 3. Clean up the coefficient in front, multiply the H's together. We get volume equals 25 pi over 432, H cubed. We do have everything in terms of H. R has now been replaced in terms of H. Part B. When the volume of the water is increasing at 3.4 cubic feet per minute. So volume of the water is increasing, so we know it's not just going to be V, it's going to be dV over dt because there's a rate involved, and it's positive because it's increasing, so we can just go ahead and indicate dV dt being the variable referring to this value 3.4. The height of the water is 2 feet, so H is 2. Find the rate, at what rate is the height of the water changing? So we're looking for not H, but the HDT because there's a rate involved here. Okay. So that's going to set us up nicely from the equation that we've gathered from part A. dV dt is 3.4, H is 2, dHdt is what we're looking for. So now we're going to start with this equation and move our way to the derivative. So 25 pi over 432, that's just a messy coefficient number that's sitting in front of the H cubed. So we'll just treat this like we would if there's a 5 or 6 or 7 sitting in front of the H. Okay, it's just going to attach itself to the derivative. We're not have to do any product rule or anything messy in terms of calculus with this number. Okay, so V becomes dV dt. Coefficient is going to stay. It's just going to attach itself to whatever this derivative is. So 25 pi over 432 stays. H cubed becomes 3H squared. And because we're asking for H's derivative, we need to attach a dH dt to indicate that each of these variables, V and H, are being affected by time, the t variable. So now that we have our derivative, we can start putting information in. H gets replaced with 2. dV dt gets replaced with 3.4. So now looks like the only thing, the only variable that we need to get by itself is dH dt because all the other variables have been accounted for. So we can just multiply all this out using our calculator. Multiply this out, 0.1818. 3 times 4 is 12. multiply this together, divide this over, use our calculator to reduce this all the way. dH/dt is equal to 1.558. Our units of measure, H is in terms of feet. H is one-dimensional unit, so not going to be square feet or cubic feet, just feet. And then there's a time involved there, so we say per minute. Part C. The radius of the surface of the water is increasing at 0.75 feet per minute. So we know the radius is dr dt is going to be associated with that 0.75. At what rate is the area of the surface? So the area of the surface here, we can tell this is in the shape of a circle. So we know we're looking for dA dt of that circle when the radius is 4.2 feet. Okay, so let's see what information we can gather here. Surface of the water, again, is referring to the shape of a circle. A equals pi r squared. dr dt is 0.75. That's the rate of change of the radius increasing. R is 4.2 at that moment in time, so we have information gathered. So now let's move towards finding the derivative. So A equals pi r squared. We find the derivative. The two variables here are A and R, so we're going to be expecting a dA dt and dr dt when we go through our derivative step. So A becomes 1 dA dt. Pi is just a coefficient that stays. R squared becomes 2r dr dt. I just put the 2 in front of the pi, but essentially it's 2r dr dt. So now we can plug information in. dr dt gets replaced with 0.75. R gets replaced with 4.2. Clean this up, and we get 6.3 pi, or 19.792. Now let's think about the units of measure here. Area is, the units of measure is, that's a two-dimensional unit, so square feet. And then T is minutes, so square feet per minute.